Episode 261 for Monday, April 16th, 2012. The technology... Sorry, I got to do it again because I broke down the wrong title. Oh! Let's try that again.
Bloopers.
Bloopers reel.
Do you want to restart the recording?
I think I will, yeah.
Okay.
Rewrite my title. And masers in astronomy. I wrote the description, but I didn't actually... Anyway, I'll be all right.
Copy and paste fail.
Copy, paste, fail. That's exactly it. Okay.
Sorry, guys.
All right, I'm ready. You ready?
Okay, yep. I'm pressing record, and
I
it's
have also
recording.
Pressed record. Okay, here we go.
Okay.
Astronomy Cast, episode 261 for Monday, April 16th, 2012. Lasers and masers in astronomy. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of University Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Abrasville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Doing really well, and I think once again I want just to remind people that if you want a really cool way that you can enjoy Astronomy Cast wherever you are in any way, to check out our Astronomy Cast app in the iTunes Store. It's $1.99 and then gives you a sort of direct feed to every episode of Astronomy Cast on demand. So you don't have to have them filling up your local drive. You can just play them, stream them directly from our server in whatever episode you want. You can go back, listen to the old episodes, the new episodes, or like my children, you can just leave it on from the time they go to bed, and it just keeps running all the way through till morning, burning our batteries. So,
and kudos to Fraser. So I have to give him a shout out because he went through and he cleaned up all the content. So it's much improved. If you've looked at it before and gone, yeah, it's fixed now because of Fraser. He's awesome.
I went through and did all the titles, and then I could see people kept saying like, "What? You guys got to fix the titles in the old shows," and I kept. And finally I downloaded it and looked at it. I'm like, oh, I see what people are driving at. I see the problem here. And so then I went through and fixed them all. So yeah, and now we'll try and improve it even some more and try and put in more cool stuff into it. So anyway, if you've got an iPhone, sorry Android people, I guess we'll talk
Not there yet.
Not there yet. But if you've got an iPhone, then $1.99. It's the best thing you'll ever buy ever.
Maybe.
All right. Well, let's get rocking with today's show. So last week we introduced the science of lasers and masers, and this week we apply that knowledge to our favorite field, astronomy. Learn how naturally forming masers teach us about the cosmos and how the artificially produced lasers help us gather better science. So just a quick recap. Last week we talked about how lasers are this concept of coherent light that is produced by, excited electrons being connected in a kind of coherent fashion?
It's induced emission. So you have an electron gets excited to a higher energy level. Sometimes it gets excited to many higher energy levels and cascades down and settles to a higher energy level. And along comes a photon with a wavelength that has an energy identical to the jump between ground state and the excited state. And as it comes along, at the exact resonant frequency, it causes that excited electron to drop down and to generate a photon that is in sync with the photon that caused the simulated emission. And
we also covered the naturally forming version of the laser, which is the maser. And
well, actually, we talked about the technology of the laboratory microwave.
We did mention that they've been discovered naturally in science too, but I guess the point is that a maser can be generated by nature, not just in the lab.
Right.
So then let's go back a bit and talk about the discovery of masers as a natural occurring phenomenon. When did astronomers first start to discover that there are actually masers out there in the universe?
Well, this happened in the 1960s. It actually happened, it was understood that it was happening after we'd been able to create them in the laboratory. So it was in 1965 that Weaver saw these really strong emission lines, and it was at a frequency of 1665 megahertz. So this is a radio frequency. And people were still trying to put together the fact that molecules can exist in space. I actually, it's one of those things where you sort of look back and you're like, why didn't we think that? And for reasons that leave me somewhat baffled, for a long time astronomers just didn't think you could have molecules in space. And this was at that point where we were still figuring this out. And so they saw this wavelength at 1665, and they named it Mysterium. Because they didn't know.
Really?
Yes, I kid you not.
Oh,
they
that's
didn't know
amazing.
what it was.
Oh, why is it not still called that? Because it was the mystery was solved.
Well, because it turned out that it was just OH. It was just the stuff that makes alcohol interesting. So it was the OH molecule, and it was attributed to coming from molecular clouds, which are these. We see them as dusty, dark regions in the sky where stars are forming. It was later found in 1969 that there was water molecules, and they went on to find CH3OH in 1970 and silicon oxide in 1974. So just over the years, we found more and more and more of these extremely bright radio sources that are extremely small. And when it comes to trying to figure out how you create something bright and small in radio, that was its own bit of perplexing stuff. And as people tried to figure it out, they realized the only thing that could be small enough and energetic enough to be producing such a bright emission line was a maser.
And so they had already, at this point, created masers in the lab.
Yes.
And so then when they saw these emissions out in space, it matched the characteristics of what they had produced in the lab. But not too far apart. I mean, we talked last week that that masers had only really been developed probably, 10 years before that?
Yeah. So this was all a fairly new discovery. People were still working to figure it out. And when they first found them in space, it was extremely confusing because to build a laboratory maser or laser, you have some sort of a resonant chamber, and you have all sorts of things that force everything to be coherent, and it's often a high pressure system. Space isn't like that. And so people had to do some really hard thinking about what would cause this. Just the idea of a population inversion required some hard thinking. So here on Earth, when you have a gas, in general, the particles in the gas are constantly colliding with one another, and as they do this, they're distributing energy between one another. And all of these collisions cause the gas to be in what we call thermal equilibrium. This is where you can describe the velocity distribution of the atoms or molecules in a specific mathematical way. And when you have a gas that's in thermal equilibrium, by definition, you don't ever have the energy inversion that you have to have in order to have a laser or maser. What I mean by inversion is, if you look at the different energy levels, you have a greater population of the electrons in the excited energy level than in the lower energy level. If you didn't have this inversion, what would end up happening is as that emission is stimulated, the emitted photon would very quickly get absorbed somewhere else, and you'd have more absorptions going on than emissions. And if there's more absorptions than emissions, the light doesn't really escape as an emission line. So you have to have this inversion of where the electrons are located. Well, in space, you don't have thermal equilibrium all of the time. What ends up happening is you have these extremely diffuse gas clouds where the atoms just don't ever collide into one another. The molecules just don't really collide into one another. And if they do, the collisions are so infrequent that you're able to have non-thermal equilibrium more often than not. And the rule of probability says you're likely to have an inversion just as much as you're likely to have a non-inversion of the energy levels.
Right. We've talked about that a bit in the past, right, where you can have situations where you've got gas clouds that are millions of degrees.
Yeah.
But in fact, you could fly your spaceship right through them, and it's not like they would be melting the hull of your spaceship. It's just that the individual particles have enough energy that it's the same as if they were millions of degrees hot. And yes, if you had it in one small area, that would be very hot gas. But the fact is you've got this diffuse gas.
So not a problem. So looking out across space, we are seeing these extremely bright, extremely small sources of emission. And as they're trying to map these things out, so okay, we can understand where the temperature not the temperature inversion, the energy inversion that's necessary comes from. It's just not in thermal equilibrium. So the next thing that we have to sort out that allows masers and lasers to exist is, how do you get all of the light coherent? We talked last week about how when you're dealing with a laser, one technique, for instance, is you only allow the light to come out one end of the laser, and so that tends to get momentum going in one direction. Momentum's not scientifically being used here, it's figuratively being used. So you're able to basically, by having mirrors around the sides of the cylinder and one end of the cylinder, direct all of this induced stimulated emission to come out one end of the laser. Well, in space, we don't exactly have cylindrical mirrored chambers generating natural masers. So the question comes, how do you end up with the nice coherent light? And it turns out magnetic fields play a very important role, where it's actually the magnetic fields are polarizing the light, lining up the electric and magnetic fields of the photons, getting all of this stimulated emission going in a coherent way through space. And,
so just to understand, I mean, we've seen all these pictures of electromagnetic fields surrounding like the Earth or the Sun, or even just bar magnets, and you've got these magnetic field lines. And another good example is, like, look at the Sun, where you see sunspots and you get these amazing, magnetic field line loops, and then you've actually got these cylinders of gas that are going from one from one sunspot to the next one, with the magnetic field acting like almost like a piece of fiber optic, channeling the gas, and then these things twist up and then snap and release the thing. So you can see there's lots of situations out in the universe where magnetic fields act like that. That's, as you mentioned, that cylinder, a capturing device, right? Is that what we've got going on here?
Well, it's not so much capturing it, it's just making sure,
holding it together?
Lining it up, lining the little soldiers up, basically. So if you've ever played with a bar magnet and iron filings, you've seen all the magnetic field lines that you can get. Well, it's not lining it up quite like the way the magnetic field lines are lining up the iron filings, but that starts to get you thinking in the correct idea. So what ends up happening is the magnetic field of the stars is capable of helping to polarize the light. So you have the electromagnetic fields lined up. You have the stimulated emission is causing new light being released to line up coherently with the last light released. And all of this adds together to allow very small localized areas around stars, around active galactic nuclei, in some cases even around comets, to have a mission that is coherent and acts in every possible way, like a laser or a maser.
And so what are the different flavors that we see of these beams? And a beam is the right way to describe it?
I wouldn't go quite that far. It's not a coherent beam like a laser that you use to torture your cat. You can actually
by shining it on the ground and letting your cat chase it, right? That's how you torture your cat, to entertain it until it's tired.
Well, it's the frustration of a failed hunt.
Fine, yeah.
Succeed in catching the laser beam.
I'm just saying that we're not torturing a cat by shooting a high-powered laser at the cat for science.
No, that's true. That's true. No, we're simply.
That's all I'm saying. I just want to clarify your definition of cat torture. So then I guess what are we seeing? When we make these observations, so we're not seeing this great big laser beam.
No.
So black hole right at us, right?
What we're seeing is pockets of gas. A star-forming region, or the area around an old star, is a great example. So you have the star in the center. It's partially responsible for the magnetic field. It's surrounded by gas that is being ionized by the star, and within this surrounding material, you have regions of different temperatures. As you move away from the star, things cool off. And so at different distances, you'll actually get different molecules excited depending on what temperature they need. Then you see also within these regions, materials are moving at different velocities. So in order to get masing to occur, masers to be observed, masing causes masers. In order to get masing to occur, you have to have a pocket of material that is all at the same velocity, so Doppler shifting doesn't cause that inducing photon to have the wrong wavelength.
Right. They need to be connected on that front.
Right. And you have to have a pocket that's all the right temperature to allow the inversion of energy levels to occur. So when we look at the gas and molecular material surrounding both young stars and very old stars, we end up seeing these different temperature regimes moving out. And what's kind of awesome is in the case of old stars that are somewhat unstable and tend to pulsate, we can use the Very Long Baseline Array. It's a set of radio telescopes that can span the entire width of the planet, basically. Using these very long baselines, we can get extraordinarily good resolution on the sky, and we're able to see that these little masing sources are moving. And we're able to see that they move in and out as the star itself pulsates. And this is an awesome way to start to get scale measurements of different regions just using geometric arguments.
Yeah, well, this is my next question, is what do we use this stuff for? What do astronomers use these masers? Now that they can detect them, I'm sure they, beyond just detecting them, they want to use them for something.
Right. So what's awesome about them is since we can't go into space with a thermometer and stick the thermometer into the gas cloud, especially when the gas cloud is extremely diffuse, what we can do is look for masing activity. We know the very precise energy levels that each of these different energy jumps takes place at. And so we're able to get a sense of what is the density of the material, what is the region based on variability that we see, what is the size of the region that's masing, and then we can also start to measure the sizes of things using a variety of different arguments. So for instance, we see these things in some cases what are called mega masers around active galactic nuclei.
Wow, I love that name.
So we basically have systems that are tens to hundreds of thousands of times more powerful than the masers that are created in the environments of stars. So that's just kind of crazy to think about. And we're able to track the rotation of the disks of material that they exist in. And we're finding that unlike the outer parts of galaxies, these internal disks of material have what's called Keplerian motion. This means that the distance that you are from the center of the disk is proportional to the rate at which you're moving in a way that Kepler's equations allow you to describe mathematically. And by knowing how heavy the supermassive black hole is in the center of that, and by measuring how fast these masers are zipping around, we can start to measure the size scale of these accretion disks and get the distance to the active galactic nuclei. So this is a check on our understanding of distance scales in the universe, where instead of relying just on Doppler shifting of how fast the recession velocity of that AGN is, we can instead go, okay, so I know how big the black hole is, I know how far away the maser is, I see how far they appear located on the sky, let's do angular stuff.
Right. Anything, so, you know, temperature, size, motion, any other things that we can use them for?
Well, I mean, clearly they tell us what molecules are out there, which is kind of awesome.
What things are made of, right, so composition, yeah.
And they're just kind of cool. I mean, it's space with lasers.
Lasers, yeah. Now, how far up the electromagnetic spectrum will the light go?
There's actually been some stars that we've been able to identify, some just within the optical wavelengths, lacing in this case, behavior taking place. But in general, we're looking out in the radio wavelengths that you could almost get with your car radio, not quite.
Right, and in infrared, in the long infrared. Yeah. So, but that's kind of exciting. So, so you've got a star that's generating a laser at almost at the red end of the spectrum.
Yeah.
but it's just, and although the wavelengths are all lined up in this kind of coherent fashion, it's not being focused like a coherent beam. So it's not like there's a star out there with a great big red laser.
No, no. And one of the things that I think has been most interesting to look at the history of this is from when we first started discovering these things. People didn't know that there were people didn't know there were molecules in space. So you start from not even knowing there's molecules in space.
Just mysterium. That's all there is out there.
Right, mysterium. To realizing, oh, there's OH, and there's water, and there's all this other stuff with increasing complexity. To now we're realizing that if you leave molecules alone in a magnetic field, they're going to mace. And so that's the other thing that these things are tracing is where there's magnetic fields, and we're finding them in neat places. Like even in supernova remnants, you'll end up seeing masers where the shock wave of the expanding material hits the interstellar media, and there's charged particles in motion, there's magnetic fields being generated, and all of this leads to masing activity.
That is really cool. Well, before we run out of time, I want to switch to the other technology, which is the lasers, and not necessarily how we're discovering them out in space, right, although I still want to find that star with a great big red laser zapping out of it, but how humans are generating lasers for use in astronomy. And I know there's sort of two interesting ones that we can talk about, and there's a bunch more, but one is using them for distance, right? We know how far away the moon is.
Right. So there's basically laser ranging. This is the same thing that cops do when they're getting ready to give you a ticket if you're misbehaving while driving down the road. So the idea is you can bounce a laser off of something, measure its distance. And if you bounce a laser off of something, and you do this over a period of time, you can get velocity both from the initial distance and the secondary distance, and also from the Doppler shifting of the light that's coming back at you. So we don't deal with the Doppler shifting with the moon quite so much, but we do get its distance down to millimeters by using pulsed laser light and measuring how long it takes those pulses to return, and that's just cool.
But partly thanks to the fact that the humans landed on the moon and carefully placed these reflectors, yes, on the surface of the moon, which then reflect a big portion of the laser light that's blasted at the moon, as opposed right to, I guess, I don't know whether you would, I'm sure the laser rangefinding would still work to some degree if you didn't have these reflectors on the moon. But
at the end of the day, you waste fewer photons, and they're literally counting 1, 2, 4 photons coming back. It's a lot of light gets lost in the process.
Right, right. And I always describe that as sort of one of my favorite reasons to know that humans did make it to the moon, which is the fact that we can point a laser and the laser will bounce off of these reflectors. And there's no way that wouldn't work if you didn't have those reflectors up on the moon. So we determined the distance to the moon. I know with accuracies, sub-centimeter accuracies, I mean, we know
really
millimeters. We know exactly where the moon is at all times.
What's
that moon
awesome,
is not sneaking up on us now.
This concept of lunar laser ranging made it into an episode of Big Bang Theory, and it's so funny because what they did, the mathematics, the physics, all of that works, but they're doing it with this little tiny telescope and a small laser. And the people who are doing this for real, they're using a 30-inch telescope, and they're using an extremely powerful green laser. They're actually using the mirror of the telescope to send the laser beam out. And yeah, so right concept wouldn't have actually worked.
Right, right. But now, are we range finding other things in the solar system?
Well, yeah, but we generally tend to use other wavelengths to do it. Again, we end up jumping down to the radio. So Goldstone radio radar facility was one of the first ways that we were measuring the distances to Mercury, to Venus, to Mars, to asteroids, and that was by shining radio light off of other nearby objects. So it's just a matter of jump around the electromagnetic spectrum until you find a friendly energy and wavelength for what you're trying to do.
And then the other and just incredible application of lasers is in adaptive optics.
Right. So in this case, for adaptive optics, ideally what you want is a nice bright star in your field of view. And you look at how that bright star moves, changes from looking spherical to looking crazy shaped, and you flex your mirror to compensate for all the things the atmosphere is doing to that starlight. Now the thing is, not every field of view has a bright star in it. But we can create bright stars by shining lasers at just the right wavelength that they excite parts of the atmosphere to ionize. So when we do laser guiding, what we're actually doing is exciting upper levels of the atmosphere to emit light that we're then studying.
And then just the technology that these great big mirrors can be modified in real time to react to the atmospheric distortions is still just absolutely mind-bending. Have you ever seen like a video, or have you actually seen this in person?
Yeah, I got to see the Observatory in person, and it's this giant honeycomb mirror with actuators all over it. And
they're like little pistons just kind of pushing on the mirrors, right? And then the mirror just kind of flexes up and down a little bit. How fast do they go?
It depends system to system, but they're looking at sub-second scales in some cases.
So these little pistons are just distorting the shape of the mirror in fractions of a second with hundreds of actuators? Thousands?
Again, it depends on the
but hundreds, yeah. And so you can imagine making these tiny little distortions in the mirror. It's a phenomenal technology, but I guess the point being, way cheaper to take a great big telescope, put in all these little actuators, fire a laser into space, than to launch it into space and get above the atmosphere. Although if you did get above the atmosphere, then it would be an even better telescope.
But I mean, the thing about keeping things on the ground that people tend to not think about is if it's on the ground, you can do experiments on your telescope. You can say, I'm not sure if this will work. I'm going to try this filter and this other thing, and that sort of learning in real time, we call it engineering time on the telescope. You get 4 nights, you don't know if you're going to get science out of them, but you're going to try a new instrument.
Right.
That sort of engineering you can't do on orbit currently.
Yeah, or you bring your own instrument that you work with a research group and you bring it to the observatory and you slot it into the telescope, replacing the CCD, and gather science in a way that maybe no one had tried before, and you won't know if it's going to work or not until you do it. So no, absolutely. So are there any other applications of lasers in astronomy? Communication, I guess, with spacecraft?
Well, so the other big thing is interferometry to tell the differences, to tell the distances between 2 spacecraft. So there's a variety of different systems. Grail, which is orbiting the moon, is one of the more famous ones, where you have spacecraft that are lacing the distance between the 2 of them, and by measuring using interference patterns how that distance changes, they can see how gravity is pulling on one before it pulls on the other to accelerate them and decelerate them in their orbits. We also see with the laser interferometry projects, we have LIGO on the Earth.
Right.
Someday maybe we'll build LISA, maybe. So this is projects where we're very carefully measuring the separation between 2 points on the ground by looking at lasers interfere. And that's the awesome thing is this is coherent light with the wavelengths of the different photons happily lined up with one another as they don't actually swim. That's me trying to imitate.
They form some kind of a wave. Well, you know what? This is great, Pamela. Thanks a lot. And I think we have 2 takeaways for today that I think if anyone can walk away with 2 concepts in their head, I think everyone should remember Mysterium
does not exist.
And megamasers.
And there are molecules in space.
And there are molecules in space. Well, that was great, Pamela. Thank you very much, and we'll see you next week.
Okay. Pausing the recording, actually stopping and saving the recording. And we will look for your questions as soon as we're done saving. And I'm actually going to close GarageBand so I can have my CPU back.
Yeah. Abandon GarageBand.
I did not.
You must.
But I use iMovie to do stuff, and when you use iMovie to do stuff, it's just friendly.
Clay Kavanagh says, Godzilla versus Megamazer. I love it. That's a movie I'd watch.
We need that T-shirt.
Yeah, Godzilla versus Megamazer. It's a pretty in joke, I think, at this point. But yeah, go ahead and ask any questions that you might have about this, about the eclipse, about the upcoming transit of Venus, Hangouts. Everyone's got access to Google Plus Hangouts now.
Yeah.
So I don't know what impact that's been having.
Today it was okay, thankfully. I think people
Yeah.
are finally getting bored with having access, and we have our servers back.
Yeah. Yeah. All the
Politely lined up is you. It's a system. Literally, there's a mirror where you're flipping back and forth between sending laser up the tube of the mirror or receiving photons down the tube of the mirror. So it's just coherent. I'm answering questions in the comment. So
we were talking about the server crashing, and then the server crashed.
irony. We had a moment of irony.
Now, I don't know if this is going to work. Do people say that they can see it?
I'm refreshing. Was it real or was it Memorex? Feed cut out just as you said that server was great. Oh, I'm seeing people say, uh-oh, I don't know if we came back. Hello, let us know if we came back. I see you, Taylor Crow wrote. Yes, Jeff says, I see it now.
Okay, we're back.
Cool.
Right, good. What were you talking about?
I was answering Dave Regan wrote in the comments, why use a telescope to send the laser beam to the moon? And he says some other things, and his thing is there a better alignment for the return? Is that the only reason? I said pretty much yes. So what happens at places like McDonald Observatory where they do lunar laser ranging is you have normal reflecting telescope. And it's a Schmidt-Cassegrain telescope. So light comes in the top of the telescope. So let me actually do tube sideways. So light comes in the top of the telescope, hits a mirror at the back. It's reflected up to a secondary mirror, reflected down through a hole in the end. And when it comes through the hole in the end, if you're in detection mode, there's a CCD there. But there's a mirror that allows them to flip back and forth between detecting things with the CCD and shining a laser through the system. And basically, by flipping the mirror back and forth, it can go from sending laser, which is just kind of awesome, and on a dusty night, you'll actually see laser through the sky,
yeah,
to detecting the light returning from bouncing off of the moon, from asteroids, from satellites. They lace lots of different things.
Right. Do you have any more questions? This is your chance about anything. Oh, we came back. So Bridget wants to know, when we talk about molecules in space, is this between stars, galaxies, and anything else, and how did they get there? So I mean, if we're talking about molecules, then did they form in stars? I mean, the carbon and all that would have had to form in stars, right?
Not necessarily. So, well, the atoms, the individual atoms.
Yeah, the atoms
form
would.
Stars.
And then they would come together.
The history of the molecules is, so originally the universe was hydrogen and helium with trace amounts of lithium and beryllium. Go listen to our Big Bang show. But over the billions of years, we've had elements created in stars. So you end up with elements up through lead, basically, created, you end up with elements up to iron, basically, created in normal stars. So carbon, nitrogen, oxygen all come from sun-like stars, for instance. And as the stars die and puff off their atmosphere, they distribute these atoms through space. And in some cases, you also have other what are called S-process atoms. These are things that are created through the slow capture of neutrons, also form in the atmospheres of stars. So you end up with a few random heavier elements. But all the really heavy stuff, so gold, silver, things like that, are formed in supernova explosions. So all these atoms get distributed through space, and they end up gravitationally clumping up in clouds, and within those clouds, over the age of the universe, very slowly, you sometimes end up with different atoms coming close enough together that they're able to bond into more and more complex molecules. We've found buckyballs, we've found chlorofluorocarbons, we've found all sorts of crazy giant molecules, and at a certain point they go from being molecules to being dust grains. And so one of the neat things is just how big can a dust grain get?
Dust grains, rocks, asteroids, planets. I mean, there's some really interesting research that's been coming out about there may be a large number of rogue planets in the Milky Way, in the galaxy. And they could have formed in various ways. Some, just as failed stars, right? But you could imagine these great big dust clouds that slowly accrete together into these just planety things.
Well, and this is where we have to look at in general, gas pressure is capable of supporting the cloud from collapsing down. And so there's this balancing point between the temperature of the gas that holds it up and the gravity of the gas collapsing it down. And once you get enough mass to go past that stability point, everything collapses gravitationally. But most clouds are quite entirely happy to support themselves just off of their temperature.
Right, right. And that's why you really want the cold gas to do it.
Well, this is where cold gas is where you see all of the molecules.
Now, Christopher King mentioned earlier on in the recording that it was great to see Pamela on The Universe. So what happened? You were on television?
Last night. Yes. So the irony of ironies, to add irony to our day, is I was on TV last night on a channel I don't get. So I haven't actually seen it yet.
No.
So I recorded with the director Colin Campbell, who does science for The Universe. I recorded an episode a few months ago called Deep Freeze, and it aired last night, and it talks about the citizen science project that we were running at the time called Ice Hunters, which has since morphed into, there's a new CosmoQuest project which also went live last night, called Ice Investigators, and how everyday people are helping to explore our solar system. It also talks about the coldest places in space, how when you freeze different liquids you end up with fish on top instead of trapped underneath the water, and things like that. It was a blast to film because we filmed it in the City Museum in the city of St. Louis. And if you're ever in St. Louis, go to the City Museum. It's a museum of found objects with a 10-story slide. It's awesome.
So did you have lots of people congratulating you on something that you haven't seen yet?
Yes, it's been very weird.
I'm sure there's a way that you could possibly get your hands on it. You know,
I'm sure, and
there's a way.
Yes.
So Jeff Morse recommends corrective optics should be called pew pew astronomy. I like that. Pew pew lasers. Jace Pearson asks, question about last night's video with Phil Plait. You guys were talking about getting together to see the 2017 eclipse. Is there a possibility that all of your brilliant minds putting together an event for anyone to come and watch with you? Yes, maybe. I don't know. I mean, we were talking about that before. You know, before we actually did the eclipse coverage and Phil had kind of jumped on and was starting to get rolling, you and I were both kind of, I don't know, what's the best way to talk about an eclipse? And in my mind, you know, the best way to present an eclipse is to go and get a really beautiful telescope stream of the eclipse, put it up, and back away from
the London Philharmonic.
Back away from the computer and let it fill the screen, and maybe get the London Philharmonic, you know, get some classical music to just play and, you know, in the background quietly, and then maybe hit a crescendo when you hit the
but I'm now thinking maximum. George Hrab and Party in the Park.
Party in the Park, yeah, a whole bunch of telescopes set up, and that might be the way to go. So it would be great, and this is going to be the most monumental eclipse really of our generation. So we should do something for it. So if you want to come, we'll think of something.
Not everyone will fit in my house. I'm only promising space for Fraser and Phil.
But I'm sure
we will arrange hotels.
Yeah, well, I'm sure there's a place somewhere along the path that maybe we can meet up that would be a good venue for it. Yeah. And I think as we're connecting all this stuff with what we're doing on Google Plus and what we're doing with our various blogs and so on, we're trying to, you know, I know Phil's putting together an outdoor event this summer, and we've got the End of the World cruise that we're going to be participating in at the end of the year.
Come cruise with us.
Come cruise with us. Yeah, if you're interested, come to astrosphere.org and you'll find some information about the cruise that we're doing. We're trying to do more of this kind of stuff, trying to gather together the community and do fun things. It's a balancing act that we need to figure out, and mostly come out of our shells. I mean, really, it's, you know, you got to put yourself out there and say, okay, everybody meet here for this thing, and then nobody shows up, and then you feel like an idiot. That's the part you want to avoid.
And for those wanting to see us in person this summer, I'm going to be at Balticon next weekend in Baltimore. Are you going to come to TAM?
Maybe TAM, yeah.
So I will be at TAM for sure.
I'm probably going to be going to the Penny Arcade Expo.
Okay, so he'll be at
PAX.
Penny Arcade in Seattle. Do you know when that is?
No. August. They all come fast and furious, right? July is TAM.
And TAM is the amazing meeting. It's in Las Vegas in July.
Yeah.
And if you go to CosmoQuest, you can subscribe to our Google Calendars, and we list all of the different events that it'll either be Fraser or me or Nicole Gallucci, or there's a whole group of us that are now working together. I love how we have bad astronomer, bald astronomer, noisy astronomer. We're bringing together a good group of people to do great things.
Yeah, and it's kind of ironic, you know, we're here on Google Plus right now, but one of the best ways to stay on top of all the stuff that we're doing is through Twitter. So if you're watching this right now, your Star Strider with a Y.
Yep.
Star Strider on Twitter. I'm Universe Today. Phil is Bad Astronomer. Nicole's Noisy Astronomer. So, you know, if you want to get the sort of updates, then you'll want to
follow us.
Our Twitter feeds, yeah.
And CosmoQuest X on Twitter posts all of it for all of us.
Yeah. So that's probably the best way. So one last issue here. Oh, you know what we didn't even talk about in the show? We should talk about lasers redirecting asteroids, but
yeah, that's not a done deal yet. It's a cool theory, so I feel okay that we left it out. It's all right.
All right.
When they've moved a rock that way, we'll still be recording. We can talk about it then.
Sure. So Jim, well, and also light sails, using a laser to move a light sail. So that's kind of cool too. So Jim Comel asks, I seem to remember lasers being used to push a dish-like object and some hints of its use as a space elevator. Heard of this? Any progress?
I haven't heard about the space elevator, actually.
I think I know what he's talking about. There was a technology that you would essentially, not an elevator exactly, you would take a train, you would put it on like Mount Fuji or Mount Kilimanjaro, and you would drive it up the side of Mount Kilimanjaro at high speed with some kind of maglev device, and then when it got to the top and launched off the top of the mountain, you would blast at it with lasers to vaporize like ice or water behind it, and that would act like thrust that would then fire it off into orbit.
That sounds like a bad idea in so many different ways.
No way! You have no imagination, Pamela. That's awesome on every scale. It's got lasers, and you're flying off mountains with trains, and yeah, no, that's awesome. I love it. You don't have to be in it, just, you know.
So the idea that seems a little bit safer that's out there is you have a spacecraft that's flying between the planets with a giant sail, and you shine a laser at the giant sail, and the laser beam, by the time it hits the giant sail, has spread out. And so the laser is on the planet Earth. The push of the laser on the Earth is not going to move the Earth. The light pressure of the laser will move the sail, and you can basically bounce things between planets this way. What doesn't work is sitting on the spacecraft shining a laser at your own sail, because the pushback on the laser is exactly equal to the push on the sail, so you go nowhere.
Have we actually, have we ever done a show on solar sailing yet?
No, we talked about it in some of the question and answer. So
yeah, we should do that.
That's something we should do at some point.
Yeah, let's do an episode on solar sailing. I'm going to write that in my big list of ideas. And you'll like that better than my other ideas that I've been giving you. Done. Okay, cool. I think we're kind of reaching the end of our hour, so why don't we wrap this up? We've answered questions. We've gone through technical issues. We've recorded an episode of Astronomy Cast. So now we still have some catching up to do, so don't be surprised if there are more episodes of Astronomy Cast showing up at random times in your feed. Thank you to everyone who is still watching. Thank you very much, Pamela, once again for letting us pick your brain about all things space and astronomy. And what's next? Wednesday, Weekly Science Hour?
Wednesday is the Weekly Science Hour. This week it's going to be Nicole Gallucci. She's going to be talking about dark skies, bright kids, and other dark skies issues with a group of people from UVA.
Awesome. All right. And when is that?
That is at 4 p.m. Pacific, 7 p.m. Eastern. And if you subscribe to our newsletter, there is a link to time zones around the world. If you don't subscribe to our newsletter, shame on you. Go set up an account at cosmoquest.org, and you can sign up for the newsletter. It's a profile setting.
Yeah, and if you're philosophically opposed to email newsletters, then
follow us on Twitter.
Follow us on Twitter, and then you'll get it. Yeah. Star Strider, Universe Today, Noisy Astronomer, CosmoQuest X. Awesome. All right. Well, thanks, Pamela. We'll see you later. Thanks, everybody.
Bye.